Chapter 5. Next stage. What to do with constants. In our equations, we have regarded x as growing, and as a result of x being made to grow, y also changes value and grew. We usually think of x as a quantity that we can vary, and regarding the variation of x as a sort of cause, we consider the resulting variation of y as an effect. In other words, we regard the value of y as depending on that of x. Both x and y are variables, but x is the one that we operate upon, and y is the dependent variable. In all the preceding chapters, we have been trying to find out rules for the proportion which the dependent variable in y bears to the variation independently made in x. Our next step is to find out what effect on the process of differentiating is caused by the presence of constants, that is, of numbers which don't change when x or y change their values. Added constants. Let us begin with some simple case of an added constant. Thus, let y equal to x cubed plus 5. Just as before, let us suppose x to grow to x plus dx. And y to grow to y plus dy. Then y plus dy is equal to x plus dx cubed plus 5, which is equal to x cubed plus 3x squared times dx plus 3x times dx squared plus dx cubed plus 5. Neglecting the small quantities of higher orders, this becomes y plus dy is equal to x cubed plus 3x squared times dx plus 5. Subtract the original y is equal to x cubed plus 5, and we have left dy is equal to 3x squared times dx. dy by dx is therefore equal to 3x squared. So the 5 has quite disappeared. It added nothing to the growth of x and does not enter into the differential coefficient. If we had put 7 or 700 or any other number instead of 5, it would have disappeared. So if we take the letter A or B or C to represent any constant, it will simply disappear when we differentiate. If the additional constant had been of negative value, such as -5 or -b, it would equally have disappeared. Multiplied constants. Take as a simple experiment this case. Let y equal 7x squared. Then on proceeding, as before, we get y plus dy is equal to 7 times x plus dx squared, which is equal to 7 times x squared plus 2x times dx plus dx squared, which is equal to 7x squared plus 14x times dx plus 7 times dx squared. Then subtracting the original y is equal to 7x squared and neglecting the last term, we have dy is equal to 14x times dx. Therefore, dy by dx is equal to 14x. Let us illustrate this example by working out the graphs of the equations y is equal to 7x squared and dy by dx is equal to 14x. By assigning to x a set of successive values 0, 1, 2, 3, etc., and finding the corresponding values of y and of dy by dx. These values we tabulate as follows. Now plot these values to some convenient scale, and we obtain the two curves in Figure 6 and 6a. Carefully compare the two figures and verify by inspection that the height of the ordinate of the derived curve in Figure 6a is proportional to the slope of the original curve in Figure 6 at the corresponding value of x. To the left of the origin, where the original curve slopes negatively, that is downward from left to right, the corresponding ordinates of the derived curve are negative. Now, if we look back at page 18, we shall see that simply differentiating x squared gives us 2x, so that the differential coefficient of 7x squared is just 7 times as big as that of x squared. If we had taken 8x squared, the differential coefficient would have come out 8 times as great as that of x squared. If we put y is equal to ax squared, we shall get dy by dx is equal to a times 2x. If we had begun with y is equal to ax to the power n, we should have had dy by dx is equal to a times nx to the power n minus 1, so that any mere multiplication by a constant reappears as a mere multiplication when the thing is differentiated. And what is true about multiplication is equally true about division. For if in the example above we had taken as the constant 1 over 7 instead of 7, we should have had the same 1 over 7 come out in the result after differentiation. Some further examples. The following further examples fully worked out will enable you to master completely the process of differentiation as applied to ordinary algebraic expressions, and enable you to work out by yourself the examples given at the end of this chapter. 1. Differentiate y is equal to x to the power 5 over 7 minus 3 over 5. 3 over 5 is an added constant and vanishes. We may then write at once dy by dx is equal to 1 over 7 times 5 times x to the power 5 minus 1, or dy by dx is equal to 5 over 7 times x to the power 4. 2. Differentiate y is equal to a square root of x minus half square root of a. The term half square root of a vanishes, being an added constant. And as a square root of x in the index form is written ax to the power half, we have dy by dx is equal to a times half times x to the power half minus 1, which is equal to a over 2 times x to the power negative half, or dy by dx is equal to a divided by 2 square root of x. 3. If ay plus bx is equal to by minus ax plus x plus y square root of a squared minus b squared, find the differential coefficient of y with respect to x. As a rule, an expression of this kind will need a little more knowledge than we have acquired so far. It is, however, always worthwhile to try whether the expression can be put in a simpler form. First, we must try to bring it into the form y is equal to some expression involving x only. The expression may be written a minus b y plus a plus b x is equal to x plus y square root of a squared minus b squared. Squaring, we get a minus b squared y squared plus a plus b squared x squared plus 2a plus b times a minus b times x y is equal to x squared plus y squared plus 2xy times a squared minus b squared, which simplifies to a minus b squared y squared plus a plus b squared x squared is equal to x squared times a squared minus b squared plus y squared times a squared minus b squared, or a minus b squared minus a squared minus b squared times y squared is equal to a squared minus b squared minus a plus b squared times x squared. That is 2b times b minus a times y squared is equal to negative 2b times b plus a times x squared. Hence, y is equal to the square root of a plus b over a minus b times x, and dy by dx is equal to the square root of a plus b over a minus b. The volume of a cylinder of radius r and height h is given by the formula V is equal to pi r squared h. Find the rate of variation of volume with the radius when r is equal to 5.5 inches and h is equal to 20 inches. If r is equal to h, find the dimensions of the cylinder so that a change of 1 inch in radius causes a change of 400 cubed inches in the volume. The rate of variation of V with regard to r is dV by dr is equal to 2 pi r h. If r is equal to 5.5 inches and h is equal to 20 inches, this becomes 690.8. It means that a change of radius of 1 inch will cause a change of volume of 690.8 cubed inches. This can be easily verified for the volumes with r is equal to 5 and r is equal to 6 are 1,570 cubed inches and 2,260.8 cubed inches respectively, and 2,260.8 minus 1,570 is equal to 690.8. Also, if r is equal to h, dV by dr is equal to 2 pi r squared is equal to 400, and r is equal to h is equal to the square root of 400 divided by 2 pi is equal to 7.98 inches. 5. The reading theta of a Fairey's radiation pyrometer is related to the centigrade temperature T of the observed body by the relation theta over theta 1 is equal to T divided by T1 to the power 4, where theta 1 is the reading corresponding to a known temperature T1 of the observed body. Compare the sensitiveness of the pyrometer at temperatures 800 degrees Celsius, 1000 degrees Celsius, and 1200 degrees Celsius, given that it read 25 when the temperature was 1000 degrees Celsius. The sensitiveness is the rate of variation of the reading with the temperature, that is, d theta over dt. The formula may be written theta is equal to theta 1 over t1 to the power 4 times t to the power 4, which is equal to 25t to the power 4 divided by 1000 to the power 4. And we have d theta over dt is equal to 100 t to the power 3 divided by 1000 to the power 4 is equal to t to the power 3 divided by 10 billion. When t is equal to 800, 1000, and 1200, we get d theta by dt is equal to 0.0512, 0.1, and 0.1728 respectively. The sensitiveness is approximately doubled from 800 degrees to 1000 degrees and becomes 3/4 as great again up to 1200 degrees. Exercise 2. Answers shall be shown in 10 seconds.